Okay, so what I'd like to talk about in this short course is a collection of topics in structural linear algebra. So let me see if everything works properly here. So I should be able to write, yes, this works, and to move to next slide. Very good. Okay, so structural linear algebra, what does that mean? So we're mostly going to talk about structured matrices. The idea is that when we give a mathematical description of a problem, and this description happens to be in terms of linear algebra, the matrices that arise from applications typically inherit a special form from the original problem. So they're not just any matrix, but they are matrices with special forms. And we'd like to exploit these special forms to perform computations in a more efficient way. The notion of structure, of course, can be interpreted in many ways. What we're especially interested in here are data sparse matrices. So what I mean here is, we all know what a sparse matrix is. This means that it's a matrix with many zeros. So the usual definition is that an n times n matrix, in order to be sparse, should have a number of non-zero entries that grows at most linearly with n. So it can be described by n parameters, which are its non-zero entries, right? It's easy to see when a matrix is sparse because, of course, it has lots of zeros. But more generally, we're also interested in matrices that appear to be dense, but actually they can be described by a linear number of parameters. So, of course, what we're thinking about here is not about single matrices, but classes of matrices. So we think of these classes of matrices where the size grows and the number of parameters grows linearly with the size instead of quadratically. So without typical examples of sparse and data sparse matrices. So the easiest example is perhaps that of band matrices, okay? For instance, tridiagonal matrices, where we have a non-zero main diagonal, a non-zero superdiagonal, underdiagonal, and everything else is zero. And more generally, matrices with arbitrary sparsity patterns. But moving on to dense matrices, well-known examples of data sparse matrices are, say, Toeplitz matrices, where the entries are constant along the main diagonal and the parallels to the main diagonal. So basically, the each entry of position ij only depends on I minus j. And the class of Toeplitz matrices then generalizes to Toeplitz-like matrices, to displacement structure matrices that obey a more general rule, a more general definition. We're not going to talk much about this. On the other hand, another class of rank structure matrices includes quasi-separable matrices and related notions. And this is what I'd like to use. This is a kind of structure I'd like to use as a leading theme in these talks. So this will be a collection of topics glued together by the notion of rank structure. So in order to clarify the framework in which we're going to move, we will consider matrices over R or C, so no finite fields. And we're going to work mainly with the goal of developing efficient algorithms to be implemented numerically in double precision, say. So, for instance, the kind of complexity we're going to look at is going to be arithmetic complexity, the number of floating point operations, rather than bit complexity. Okay, so what do we do with structural matrices? So typical tasks include, of course, matrix operation, basic operations. We'd like to multiply, to be able to multiply a matrix times a vector, to sum two matrices, to multiply two matrices, to invert a matrix. We'd like to solve linear systems. We compute matrix factorizations like LU or QR, compute eigenvalues, compute matrix functions, or solve matrix equations. On this topic, it's important to note that a good desirable property for a class of structure matrices is to be closed with respect to the main operations we perform on matrices, and mainly inversion, but also sums and products. So we'd like our classes of structure matrices to be designed so that when I take a matrix in the class and I invert it, I am still in the same class. And so I can still use the same representation, data sparse representation I defined at the beginning. Okay, so a quick outline of this short course. There will be two parts. What I'd like to do today is to give a quick introduction of notions of sparsity and what we're going to use and what we're not going to use. And I'd like to talk about a topic that's been treated extensively in the literature, but I think it's fascinating and it deserves a place, and that's eigenvalue computation for continuum matrices, and so root finding for polynomial, numerical root finding for polynomial through eigenvalue computation and its generalizations. Tomorrow, on the other hand, I'd like to move on to functions of structure matrices. So we'll see that more about that tomorrow. Okay, so let's start with a few examples. So as we were saying, band structure is a classical example of matrix structure. Here we have a well-known example, which is the finite difference discretization of the one-dimensional Laplace operator, so second derivative. This is a tridiagonal matrix. So it only has non-zero entries whenever the difference, the absolute value of the difference between the indices of the entries is 0, 1. And band structure is typically associated with locality properties. By this, I mean that we're working on a system where we have a collection of objects or of nodes in a discretization, where each object or each node only has an influence on its neighbors. And it does not have an influence on nodes or objects that are far away. For instance, here in the discretization of a differential operator, what we perform is a discretization of the space where we're working, which is the real line or a segment. And of course, since we have a second derivative, we only have relationships between nodes that are direct neighbors or at distance 2, and that gives us a tridiagonal matrix. Here's another example from physics, again, in order to illustrate the relation between band structure and locality properties. In this example, we take a physical system, which is hydrocarbon molecule. Okay, so in a hydrocarbon, what we have is a chain of carbon atoms, okay, the ones in black. Here we have a small example, the one of the matrix is larger. And there are bonds between these carbon atoms. And moreover, each carbon is linked to two hydrogens. Okay, the white atoms are hydrogens. And on top of this, we have one hydrogen at the beginning of the chain and another hydrogen at the end of the chain. Okay? So, well, this is a small example in the picture. This is octane, but the system we consider here has 52 carbon atoms and 106 hydrogen atoms. So it's interesting in some physical applications in order to model the behavior of such a system, to write the Hamiltonian matrix. By this, I mean the discretization of the Hamiltonian operator, the energy operator of the system. So kinetic energy plus potential, right? We're interested in writing the matrix that discretizes this energy operator for our system. Because then by performing certain kinds of computations on these matrices, we derive many interesting properties of our system. Of course, we need to choose a basis, and one possible choice is our basis of atomic orbitals. So what we have are functions, basis functions that have limited support, which are centered on each particle in the molecule. Okay, and so physical intuition tells us that in such a system, each atom will have an influence on the atoms which are close to it. For instance, this carbon here will exert an influence on the hydrogens here, on the carbons here, then also on the on these other particles. But it will have little influence on atoms which are far away. Okay, and this physical intuition is reflected in the shape, in the structure of the Hamiltonian matrix associated with the system. So this is the matrix, which is size about 680 times 680. And in this plot, I have used different colors to indicate the order of magnitude of the elements. So darker colors like black or dark blue here means larger magnitude, larger elements. And lighter colors like light blue and yellow means that the magnitude of the entries is decreasing. And so what we see is that close atoms have a strong relationship, strong influence on each other. And on the other hand, as the distance between atoms increases, and so we're moving away from the main diagonal of the matrix, the magnitude of the entries decreases very quickly, and until we have this white part that's basically negligible. It can be approximated by zeros. And so what we have is an approximate band structure that reflects the locality of the system. Of course, the structure of the matrix also depends on the choice of bases. If we had chosen, instead of this localized basis, a different kind of basis with functions which are spread out over all the space, maybe we might have had different results. Okay, and then what about more general sparsity patterns? So an application that's very widespread nowadays, much studied in the last years, and perhaps we'll mention it tomorrow, is the use of linear algebra to study complex networks, complex systems, which are modeled by graphs. So here's a very simple example, which is beloved of authors in these fields. So what we have here, think of it as an early example of social network, is a network associated with notable families in Florence in the 15th century. Okay, so here you see a few well-known names, starting with this one. And so each node in this graph corresponds to one family, and links between nodes correspond to marriages between the families. More generally, if we have a network, say, think of a social network, think Facebook, for instance, where we associate a node with each user and links to relationships between users, for instance, friendship between users, we can derive useful properties of the network by working on the adjacency matrix of a graph. That is, the matrix that has size n by n, where n is a number of nodes, and has entry ij equal to 1 if there's a link, an edge between nodes I and j, and 0 otherwise. Okay. This is typically a sparse matrix because the number of links, the number of edges tends to be small with respect. So we typically don't have complete graphs, right? So the number of edges in real life networks tends to grow linearly with the number of nodes.
And so we have a sparse matrix with a sparsity pattern that's not always easy to predict. We don't necessarily know it in advance. But what we know is that sparsity allows us to perform some operations in a fast way. For instance, matrix vector multiplication can be done efficiently. And so O of n operations instead of O of n squared. And as a consequence, Krylov methods, which are based, like Lanczos and Arnoldi, which are based on matrix vector multiplications, are widely used in on this kind of applications. Then I'm not going to say much about Toeplitz matrices, but at least one or two slides cannot be avoided. Obviously, this is a very important chapter in the on the topic of structure matrices. So Toeplitz structure tends to arise from shift invariance properties of the system. And as an example, I'd like to show blurring models for signals and digital pictures, digital photos. For instance, here we have a picture of the Hubble Space Telescope. And here on the right, we have a blurred version of the same picture. By the way, I generated this blurred picture using a nice method toolbox for image manipulation and restoration. That's called IR Image Reconstruction Tools by Gazzola, Hansen, and Nagy, who are specialists of these topics. And it's very nice and user-friendly, so I highly recommend it. And the way this blurring is done, the way this blurring model works, is by convolution with a so-called PSF. PSF stands for point spread function, and that's the image, the blurred image of a single white pixel in a black background. So if we assume that the blurring operator is invariant with respect to translation in space, so if we assume that blurring works the same way here and the same way here and the same way here, what we have to do is to choose how this blurring works. So it will be a convolution. So think of it as a weighted average of a pixel with values of nearby pixels. And then we apply this convolution to all the pixels in the picture. And that's how a blurring model works. Then the actual problem is to invert this model and start from the blurred picture and go back to the original one. So this is a typical class of problems where we have to deal with Toeplitz and associated structures. So for simplicity here, we have a one-dimensional case where we have a signal more than a picture. So the convolution operator in its continuous version is written as an integral, right? So if x of t is our signal, depending on time, and P is the convolution operator, the convolution kernel, so the PSF, basically. The blurred signal is obtained as a convolution of P and X. And when we discretize this, what happens is that we have a vector X containing the discretization of our signal X of t, or a function X of t. We have another vector B, which contains the discretization of the blurred signal, and the operator that acts on the original signal and gives us the blurred one is a Toeplitz matrix. Because when we apply discrete convolution, what we're doing is to perform basically a weighted average on each of these entries, right? And the coefficients of this weighted average are the same for each xi. And for this reason, we obtain a Toeplitz matrix. So in this sense, Toeplitz structure is associated with shift invariance and is reflected in the shape, right, of the matrix. There was a few years ago, in 2014, another course on structured linear algebra, which was given by Dario Bini, and he gave a large part of his presentation on Toeplitz and displacement structure. So I certainly won't repeat this, but I had to mention it. And another thing he talked about were eigenvalue problems for linearization of matrix polynomials. That's something else we won't talk about today, but we'll just mention relevant topics for our discourse. So let's now move to quasi-separable structure, which will be the leading theme that guides us today and tomorrow. So what is quasi-separable structure? So basically what this means is that I have a matrix. This matrix has an upper triangular and a lower triangular part. And I say my matrix is quasi-separable if every time I extract a submatrix from either from the upper triangular part, so like this, or from the lower triangular part, so like this, of my matrix, these submatrices, these blocks, have low rank. Low rank means bounded by a number which is small with respect to the size of the matrix. Again, if we think in perspective for matrices that increase their size, typically what we'd like is that the ranks of these off-diagonal blocks stay uniformly bounded. This kind of structure can be seen as a generalization of other structures in different ways. It's certainly a way of extending the class of low-rank matrices, right? So low-rank matrices are delta-sparse matrices, because of course we can write them as a product of tall and skinny matrix times wide and low one. If we split the structure and think we have one kind of rank K of low rank structure in the upper triangular part and another kind of low rank structure in the lower triangular part, then what we obtain is a quasi-separable structure. It's also an extension of the class of banded matrices, because it's easy to see that if you have a banded matrix, that's a quasi-separable matrix, okay? But banded matrices have the problem that if you invert the banded matrix, you do not get an exactly banded matrix, whereas quasi-separable matrices are closed with respect to inversion. So in that respect, that's an improvement. Historically speaking, quasi-separable structure was born from the discretization of the integral equations, integral kernels. If you have you could have an integral kernel, a bivariate function that's separable, because you can write it as a product of two functions, two univariate functions in the different variables. So think f of x times g of y. And the discretization would give you a rank 1 or low rank matrix. A generalization of this approach gives us a quasi-separable structure. Another point of view that will not insist about this, but it can be interesting, there's a series of papers by Bela, Olszewski, and Zlobich, presents quasi-separable structure as a generalization of the structure of recurrence matrices for orthogonal polynomials. So typical three-terms relations for orthogonal polynomials, think Chebyshev or other examples, will give you, say, tridiagonal Jacobi matrices, and these are certainly quasi-separable. But in other examples, like Sego polynomials, you might get upper Hessenberg unitary matrix. And this is also quasi-separable, as we will see in a moment. So in this respect, we can also see quasi-separable structure as a generalization of structure of recurrence matrices for classes of orthogonal polynomials. Okay, so let's see an example in more details and the definition in more detail. So suppose RL and RU are positive integers. We say that an n times n matrix M, which we assume to be complex in general, could be real, is RL, RU quasi-separable of orders of quasi-separability ranks RL, RU, if all the submatrices taken from the lower triangular part of the matrix have rank at most RL, and all the submatrices taken from the upper triangular part of M have rank at most RU. Okay, so I'm using here a MATLAB-like notation where, so this expression means
the submatrix of M with rows have indices going from k plus 1 to n and columns 1 to k. Okay, so these are clearly blocks from the lower triangular part. And same thing for the upper triangular part. Okay, so here we have rank at most RL, and here we have rank at most RU. So as we were saying, banded matrices are a classical example of quasi-separable matrices. Here we have the same example we had before, or the one-dimensional Laplace operator. So it's easy to see that all the off-diagonal blocks have rank 1, okay? Because of the sparsity, right? We only have one non-zero entry, okay? So this block in red, if we look at the lower triangular part, this block in red has clearly rank 1, and also this block in red has also rank 1, and the same is true for the upper triangular part. But if we look at the inverse of this matrix, which is this one, this is not sparse, this is not banded, this is definitely dense, but it's still quasi-separable. So if we look again, for instance, at this block, it's easy to see that the second column is 2 times the first one, right? So clearly rank is 1. And also in this block, the first row is 2 times the second one. So again, rank is 1, and the same for the upper triangular part. So inversion preserves quasi-separable structure, even though we lose sparsity. So how do we work with quasi-separable matrices? So the point is here that an n times n matrix of quasi-separable order R can be represented by O of n parameters, a linear number of parameters. The dependence on the quasi-separable order in our examples will be quadratic. Okay, so O of R squared n parameters. And for this reason, one is able, hopefully, to design fast algorithms that are specifically tailored to quasi-separable matrices. Because you no longer have to deal with n square entries, you can work directly on these O of n parameters. Okay. In particular, it's useful to observe that the inverse of a quasi-separable matrix is again quasi-separable of the same order, and sums and products of quasi-separable matrices are again quasi-separable, but unfortunately, this time the orders are not preserved. What we have is that the sum or the product has as quasi-separability order the sums of the orders of the terms or the factors. So that means that in a quasi-separable algorithm, we can perform inversion as many times as we want, and we'll still get a quasi-separable matrix with the same representation, same structure we had at the beginning. We can perform sums and products, but we have to be careful. We have to use them sparingly, because each time the quasi-separability orders might increase, and so the complexity of the algorithm risks increasing if we don't bound the number of sums and products. Okay, so on this theme, I'd like to mention another kind of representation for quasi-separable and related rank structure matrices. That's known as HODLR representation. HODLR is an acronym that stands for Hierarchical Off-Diagonal Low-Rank Representation. What does this mean? It's a recursive block representation that is used for rank structure matrices, and in particular can be used for quasi-separable matrices. It was introduced by Hartbusch in actually in a larger framework of hierarchical matrices and representations for such matrices, stemming for instance, differential equations. So what's the main idea in this kind of representation? So suppose we have a matrix that's of size m times n and has quasi-separability order k. Let's partition it in 4 blocks. Okay, so we assume here that the diagonal blocks are square, the off-diagonal blocks need not be square. Okay. So if A is quasi-separable, what happens? Well, it happens clearly that by definition, this block and this block have rank K, right? So they can be represented in a compact way, right? Again, in the way we saw before, tall skinny matrix times a matrix that has the transpose size. On the other hand, A11 and A22 are, again, they don't have low rank, but they are, again, quasi-separable of order K. So we can iterate this partition and compress procedure recursively until the diagonal blocks reach a certain predefined small size, we call M min, and at that point, when this is small enough, we can store them as full matrices. Okay, so here's a picture. So we start with a full matrix, we partition it in 4 blocks. We show in gray the low rank blocks, okay, that are singled out at each step. So we store them easily as low rank matrices. So this and this are done. Oops, sorry. Okay, we have taken care of this and we have taken care of this. We're left with the white blocks. What do we do with the white blocks? We iterate our partition process. So we divide it in 4 blocks. And again, this has low rank, this has low rank, same here. And so we're left with these white smaller blocks, and we iterate again, and so on and so forth, until the size of these blocks is small enough. And at that point, we store them as regular full matrices. So what is the storage cost for this kind of representation? Well, for each submatrix, if we assume that, that the quasi-separability order K and the minimum size, the final size and min are negligible with respect to the size of the whole matrix, then the storage cost for each submatrix is of the order of m. And since we have O of log n recursive steps, the total memory requirement for this kind of representation is of the order of m log n. And it turns out that one can perform basic operations on matrices written in this way, represented in this way. The advantage is also that the operations can be performed adaptively with respect to the ranks of the off-diagonal blocks. So if some blocks happen to have lower rank than expected, this property can be exploited because of the more compact representation. And so we can perform basic operations such as matrix vector multiplications, matrix multiplications, additions, inversion, and linear system solving in O of m log m or log m square operations. And the dependence on the quasi-separability rank is quadratic. There's a nice toolbox, a MATLAB toolbox for dealing with these matrices called HR Toolbox by Stefano Massei, Leonardo Robol, and Daniel Kressner. Okay, so back to our quasi-separable matrices. In fact, the representation I'd like to use perhaps more in this presentation is a so-called quasi-separable generator representation, which works in the following way. This is the one I'm going to present was introduced in 1998 by Aidan Yuri Animal and Israel Goldberg. And it uses O of NL square plus NU square times big N parameters. So linear in the size of the matrix and quadratic in the quasi-separability order. Yes, absolutely. Thank you. Thank you, Xavier. Yes, this is typo. Okay, so this is RL square, obviously. And this is RU square. Thank you. So lower quasi-separability order and upper quasi-separability order.
Okay, so here we have the definition we saw before. How do we represent quasi-separable matrices? So what we do is we are going to use, we represent separately the diagonal on its own. So we have parameters and parameters for the diagonal entries. And then we represent separately the lower triangular part and the upper triangular part, okay? So in each of these, so one here and one here, upper and lower. And in each of these triangular parts, we're going to use as generators a collection of row vectors, which will be the PIs or the GIs, a collection, so the length of these PI or GI is RL or RU. Let's call it R. Let's simplify our notation and assume that RL is equal to RU is equal to R. Okay, so R quasi-separable matrix. So these PI are row vectors of length R, okay? Then the we have a collection of matrices, let's call them AJ. These are R times R. And then we have a collection of, so wait, we'll call this K maybe. Okay. And then we have a collection of column vectors, which are the QJ, vectors of length R. So again, these are small, vectors and matrices of small size, right? And each entry is represented as a product of one row vector times a certain number of matrices times a column vector. So we have a set of row vectors, matrices, and column vectors for the upper triangular part, and another set for the lower triangular parts. There are n, or n minus 1 of each. So in total, we have O of n objects, and therefore O of n parameters. Here's a picture that maybe explains better what I'm trying to say. So each off-diagonal entry of n is represented as a product of these generators, of these building blocks, taken from a set of O of n items. So a row vector times a few matrices times a column vector. So for instance, the entry of indices 4, 1 is represented as P4 times 2, so this is again R, right? R by R matrices times 1 column vector of length R, which is Q1. So note the way indices work. So this is P4, 4 like the row index. This is Q1, 1 like the column index. And the matrices, the two matrices in between, fill in the missing indices, 4, 3, 2, 1. Okay. So we have this collection of row vectors, P1, P2, P3, up to n, collection of column vectors, Q1, Q2, Q3, and so on, collection of matrices, A1, A2, A3, A2 actually, and so on. And picking from the set of generators, we can represent all the upper triangular, all the entries in the upper triangular part or in the lower triangular part. So n square objects, all of n square objects. Here's an interesting example, unitary upper Hessenberg matrices. So first of all, what does upper Hessenberg mean? Upper Hessenberg structure means that the matrix has 0 below the first under diagonal. So every time the row index is larger than the column index plus 1, then we have a 0. And this is a sparsity pattern that results. This is called upper Hessenberg structure. Okay. So we're interested in the case of a matrix that's upper Hessenberg, and in addition, it's also unitary. Oh, sorry, so this will be C and N, right? So it could be R and N and orthogonal, or C and N and unitary, right? So I'm going to denote with an asterisk with transpose conjugates. And so I have U star U equal U star equal identity matrix. So what can we say? So clearly there's a sparsity pattern here, but what can we say about the ranks of blocks taken from the upper triangular part of this matrix? In fact, so upper Hessenberg structure in itself says nothing about these ranks, but if we add this condition, we can say something more. So here the nullity theorem will come to our aid. Nullity theorem, I'll take a moment to say a few words about it. It's a fascinating result, I think. It's surprising the first time that you see it. So we call nullity of a matrix the dimension of its null space, of its kernel, right? So there is a theorem by Fiedler and Markham, which says the following. Let R an n by n invertible matrix. It could be also complex, of course. And let's call B the inverse of A. Then let's consider block partitions of A and B like this. So these block partitions can be, the block partition of A can be done as we want. In particular, A11 does not need to be square. It could be rectangular, okay? On the other hand, the partition of B must be the transpose of this partition, because we want to be able to multiply these matrices by blocks. Okay. So, for instance, if A11 has size P times Q, then B11 will have size Q times P. Okay. Then the theorem says, in its simplest form, that the null space of this block has the same dimension as the null space of this block. Okay, this is not difficult to prove. Here's a quick sketch. We can suppose that the nullity of A11 is smaller or equal to the nullity of B22, because otherwise we could just apply a permutation and go back to this case. We can also assume that n of B22 is strictly positive, because if it were 0, then also the nullity of A11 would be 0, and then we would be finished. Then there exists clearly a matrix F with n of B22 independent columns, such that B22 times F equals 0. Because if B22 has nullity n of B22, then it's able to kill at most n of B22 independent columns in a product, right? So if we multiply these two matrices, which must yield the identity matrix, we obtain in particular these two relations, right? This for the off-diagonal blocks and for the off-diagonal blocks of the product, and these for the diagonal block, one diagonal block of the product. If we multiply them by F, okay, clearly all the terms containing B22 are 0. And so we are left with A11 B12 F equals 0 and A21 B12 F equal F from here. Now, clearly this implies that the rank of this matrix is larger or equal to n of B22. And at this point, using this relation, we have the nullity of this block is larger or equal to the rank of B12F, which is in turn larger or equal to n of B22. Okay, and what is nice is that we can easily generalize this result. So the initial result was just for this block and this block, but if we apply suitable permutations to our matrices, we can easily generalize this result. And so in particular, what we have is not only that n of A11 is equal to n of B22,
and the same for the other two diagonal blocks, but also that the nullity of this block is the same as the nullity of this block. And again, the nullity of this block is the same as the nullity of this block. Okay. So this theorem is usually attributed to Fiedler and Markham, who published it in its more or less in this form, and it's and the form it's mostly used nowadays. But there was an original work by Gustafsson who gave a formulation in terms of matrices over principal ideal domains. And there's also a very nice presentation by Van der Briel and Van Barel, who give alternative proofs and illustrates the use of this theorem in structure matrix algebra, in structure linear algebra. Okay, so if we apply this property to our upper Hessenberg matrix, so in our upper Hessenberg matrix, we have 0 blocks here, okay? And this means, this gives us a result on the nullity of blocks in this position in the inverse, but the inverse is a transpose. So we have results on the nullity of the off-diagonal blocks in the upper triangular part of our unitary matrix. And so what we can conclude is that a unitary upper Hessenberg matrix is such that all blocks taken from the upper triangular part, including the diagonal, have rank at most 1. So this is a one quasi-separable matrix, but it's even more than that because we can include the diagonal in the block structure. And so the quasi-separable representation, the way we saw it for such a matrix, looks like this. So we have below the main diagonal, we have these entries which restore separately these sigma, and below the sigma there are zeros because of the upper Hessenberg structure, and then the upper triangular part, as you can see, is represented using the generator representation we saw before, and here we don't really have vectors, we have numbers, okay? So we have G times a few matrices, which are again numbers, times H, okay? So the row vector times the matrices times the columns, right? Column vectors. They're all numbers in this case. Okay, this representation can also be generalized to the block case. So if we look at our matrix as a block matrix, we can use a block representation where, well, everything works as above, but now the sizes of the generators are no longer just columns, column vectors and row vectors in addition to matrices, but the sizes may depend also on the sizes of the blocks we're using, okay? Well, I won't dwell too much on this because we're not going to use it. I'd just like to mention another kind of representation that's been used for quasi-separable matrices. This was used mainly by the group in Leuven, by Van Barel, Van der Briel, and so on. It's also used in their 2 books on quasi-separable matrices. It's called the Gibbons vector representation. And so, as the name says, what is done here is that matrices, quasi-separable matrices, semi-separable matrices, as they call them, are seen as identified by a sequence of Gibbons matrices together with a vector. So, what is a Gibbons matrix? Gibbons transformation is an orthogonal or unitary 2x2 matrix. So in the real form, we can look at it as cosine of a certain angle minus sine, cosine, right? So it can be seen as a rotation. But more generally, we can look at Gibbons transformations as unitary or orthogonal 2x2 matrices. Gauss transformations are widely used in linear algebra because they can be applied to zero out specific entries or a vector of a matrix. Okay, because if we have any vector xy, so length 2, we can find a Gauss transformation that puts a 0 here in the second position, right? In the first position, we're going to have the norm of the vector because the matrix is unitary or orthogonal. So let's take a quick look at how this representation works for a semi-separable matrix, meaning a 1-1 quasi-separable matrix with the main diagonal as part of the rank structure. Okay, so the unitary matrix we had before was an example of this. The way this works is like this. So the representation is made up of a sequence of n-1 Gauss transformations and a vector. So we call the entries of this vector v1, v2, vn. How does this data encode a lower quasi-separable structure? Let's look at the example. Here's how I build my the lower triangular part of my matrix, starting from the Gauss transformations and the vector. So I start by writing the first entry of the vector in the upper left corner of this empty matrix. Then I apply G1 on these two rows. And what happens is that I obtain two non-zeros here and here in the first column. Then I take the second entry of my vector and I put it here in position 2, 2. And at this point, I apply G2, the second Gauss transformation, to the second and third row of my matrix. And so I am adding non-zeros here and here in the third row. Then I add V3 in position 3, 3, and apply G3 here, sorry, not here, but here to the third and fourth row, and so on and so forth. And this way, I unroll, this expression is often used in these contexts, I unroll the lower triangular part from the vector, okay? And you can easily imagine how the representation was built. So one starts from the lower triangular part and looks for a Gauss transformation that puts zeros here because we know that this submatrix has rank 1. And then, so in this way, we obtain D5, and then we look for a Gauss transformation that puts zeros here because this matrix has low rank, and so on and so forth. Right? And so the matrix defined in this way has this kind of form. You can see that if you look at it this way, it resembles a bit the generator, a quasi-separable generator representation, right? So we have this product of entries in the Gauss transformations, the sines and cosines, and the entries of a vector. So the upper triangular part is represented in the same way, and storage is also very convenient because if each Gauss representation, each Gauss transformation can be represented by sine and cosine of an angle, then we can just see it as a 2 times n-1 matrix. Okay. One could also just store the angle, but from a numerical point of view, it's better to keep the cosine and sine. If we want to also add a diagonal that's independent from the independent of the quasi-separable structure, then we had an additional set of n parameters. So the total storage is 5n plus constants. Okay, so this kind of representation, as I was saying, used in the books by Van de Bril and Barrel and Mastronardi, who develop all sorts of algorithms for working with this representation. Okay, so as we were saying, the kind of operations we want to perform and the kind of algorithms we have available concern matrix vector multiplication with structured quasi-separable matrices, matrix multiplication, LU and QR factorization, so lower triangular times upper triangular, or unitary times upper triangle, right? Matrix inversion and solution of linear systems is once we have LU or QR and we know how to invert triangular matrices, this is comparatively easy to do. And there are also algorithms for eigenvalue computation concerning several subclasses of quasi-separable matrices. And we're going to talk about this more in a moment. Why do you need orthogonality of the given matrices? Okay, so in principle, you can certainly do everything without orthogonality. So the matrices can be anything, not necessarily orthogonal. But since we plan to use these representations numerically, it's always good to use orthogonal and unitary transformations as much as we can because they're well conditioned. They won't spoil, they won't amplify the errors in the quantities you're working with. So if we develop these algorithms with the idea that they will be applied in floating point computations, so if we assume that there are errors in our computations, we must be very careful not to, as much as possible, not to amplify these errors in the course of computations. And non-unitary, non-orthogonal matrices can be sometimes a bit risky because they can amplify the errors. Whereas unitary and orthogonal matrices are perfectly safe. We can apply them as much as we want, and they won't spoil the results. Over finite fields, you mean algorithms for quasi-separable structure? So we first need to take a look at what it means to have a quasi-separable structure in a finite field, because you would use the same definition, I suppose. And then, I'm not sure everything is going to work in the same way when you have a positive characteristic. We should think where this might fail. I think that the usual algorithms could probably fail somewhere. I need to think a little about this. It's a very interesting question, and usually this is all of this is developed with the idea of working over real and complex examples and cases. But application to finite fields, we should check whether there are some passages in the proofs that require zero characteristic, and I think there are. But I should check. So thanks for the question. That's a good food for thought. Yes. And speaking of use of quasi-separable matrix, I'd also like to mention work by Clément Pernet, who used the quasi-separable structure in relation to the rank profile matrix, and an ISAC paper, and then another GSC paper in 2018. So that there are many uses for this kind of structure. Okay, so a topic I'd like to say something about is the usual use of eigenvalue computations for structure matrices and quasi-separable matrices with the goal of computing roots of polynomials. So there's quite a bit of literature on this topic that's been treated extensively. I'll just say a few words, give a few pointers. So this is the problem. We have a polynomial with real or complex coefficients. Let's assume for now that the polynomial is monic. So leading coefficient is 1. It's well known that an equivalent problem is to compute all the eigenvalues. The equivalent problem to, finding the roots of this polynomial is computing the eigenvalues of the associated Frobenius companion matrix. Okay. So when I talk about computing, of course, I mean approximate numerically. This approach turns out to be quite effective, and its use in the MATLAB command roots is very celebrated. So it's often used as a standard for polynomial roots computation in certain software systems. Not always, of course, but it's an interesting avenue. So the way this is usually done is through the so-called QR method. The QR method was proposed in the 50s independently by Francis and Kublatnovskaya. And the way it works, so it's called QR method because it's related to the QR decomposition. And the way it works is, so this is a general purpose iterative algorithm for computing eigenvalues of a matrix. And the way it works is reduce the matrix in upper Hessenberg form by unitary, by similarity with a unitary matrix. In our case, the companion matrix is already in upper Hessenberg form because we have zeros here, right? We don't need to perform this preliminary step. And then at each iteration of our method, what we do is, so we start with from a current iterate ak, and what we do is compute the next iterate ak plus 1, which is given by qk star times ak times qk, where qk is a unitary factor in the QR decomposition of ak. So if we take ak, we compute its QR decomposition, unitary times triangular, upper triangular. And then we use this matrix in this way. We generate a new matrix, aak plus 1, which has clearly the same eigenvalues as ak, okay? But the interesting thing is that typically, this iteration converges to a triangular matrix. Okay, it starts from upper Hessenberg. So upper Hessenberg has this kind of structure, right? There's an this is the main diagonal, and this is a subdiagonal. It starts from this structure, and the iteration preserves the upper triangle, the upper Hessenberg structure, and tends to put zeros here and leave an upper triangular matrix. And of course, once we have an upper triangular matrix, the eigenvalues are on the diagonal. So this has been proven to be backward stable, meaning that it computes the eigenvalues of a matrix which is close to the starting matrix. Okay. Of course, we don't know if the computing eigenvalues are actually close to the exact eigenvalues. This also depends on the conditioning of the problem. Eigenvalues can be ill-conditioned, in which case there's not much we can do. But backward stability, which is what we can aim for, holds in this case. So typically for a general matrix, the cost of this algorithm is n squared, O of n squared, because it typically requires O of n iterations, and each iteration costs O of n squared operations, and storage is O of n squared. So if we have very large matrices, the cost of this algorithm can grow very, very fast. So if we have a polynomial of large degree, using this approach to compute its roots can be costly. But we can exploit the special structure of the companion matrix. And in this way, it's possible to reach a computational cost of O of n operations per iteration, the linear memory space. And so overall, a cost of O of n squared operations. Why is QR? Each iteration is O of n squared, each iteration, because what you do is, I'm going to explain it in a moment. Okay, I'm going to explain the procedure in a moment. Or maybe
we can go straight away to the way it works. Okay, so the usual unstructured implementation is actually unrelated to the QR decomposition. We don't really compute the QR decomposition, at least in the usual implementations. We don't really compute the QR decomposition of the matrix. What is done is the following procedure. We apply, at each step, we apply the Q matrix as a sequence of 2x2 unitary matrices. Okay. And each of these 2x2 matrices is determined through a process called bulge chasing. So in practice, this is how it works. We have to choose a unitary 2x2 matrix to start with. And I won't go into the details, but this is chosen taking in consideration also the so-called shift strategy. Okay, in practice, one does not apply the algorithm to the matrix A, but to the matrix A minus a multiple of the identity, or to a certain polynomial in the matrix A, because this improves convergence. So we start with a certain 2x2 unitary matrix Q1, and we apply it on the first two rows of the matrix. Okay, so the cost of this is roughly n, right? O of n. Okay, so we actually apply Q1 star. Okay, so in this notation, what I mean is Q1 is a 2x2 matrix, unitary, and Q1 star, Q1 tilde, sorry, is this 2x2 matrix embedded in a larger identity matrix. So what is x, 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 and then 1, 1, 1. Here are zeros and here are zeros. Oh, this was supposed to be a 0. Okay. The tilde notation is just to make dimensions work. Okay, what I'm saying is that I am applying Q1 here. This has a cost of O of n, okay? And I'm going to do it n times. So that's why n squared cost comes up, okay? Okay, so if I apply Q1 on the left with a star, I also have to apply it on the right. And when I apply it on the right, I'm going to act on these two columns. And this is going to put a non-zero here, okay, like this. So I have this non-zero here. This is called a bulge because it's a deviation from the usual upper Hessenberg structure. So at this point, we have a matrix that's similar to the previous one. It has the same eigenvalues, but it's no longer upper Hessenberg because it has a bulge. So we want to eliminate the bulge. And so we look for another 2x2 transformation called Q2 that acts on the second and third row and puts a 0 here. Okay. Like this. Now we have a 0. But since we have multiplied by Q2 star here on the left, we also have to multiply on the right. And so perform a combination of these two columns, and this gives us a bulge here, right? Like this. And so on and so forth. That's why it's called bulge chasing, because the way the matrices are determined is by chasing this bulge, pushing it down along the matrix. So we keep multiplying by 2x2 matrices and pushing the bulge down until we arrive to the end of the matrix. And so we have Q4 here, Q4 on the right that adds the last bulge, and then Q5, and Q5 will not spoil the Hessenberg structure, right? So that's the way it's usually implemented, okay? That's why it costs n squared. So the thing is, we'd like to do this in a structured way, okay? So as I was saying, there's quite a bit of literature on this. And in the beginning, what people tried to do
was to use the so-called explicit QR. Explicit QR means actually computing at each step the QR, the composition of each iterate, okay? It's a way of doing it. It's technically equivalent, but it's not efficient. So the first attempts in this direction were done like this. Then people moved to the so-called implicit QR. That's QR as I presented it with a bulge chasing. That's more efficient. And there's been quite a bit of literature, and basically each group has tried to develop their own version of bulge chasing with different representations. So there were versions with the so-called sequentially semi-separable representation by Chandrasekhar and collaborators. And our group also did some work on this with a quasi-separable representation. And the group in Leuven also used the Gibbons vector representation I told you about before. And then a very interesting development happened in recent years, starting 2014. There's a nice book about this by Orens, Bach, Robert, Van de Briel, and Watkins. So it was David Watkins that initiated this approach together with the Belgian group. And the idea is to rephrase again the representation in terms of core chasing algorithms. I'm going to say a word about this in a moment. That proves to be efficient because in addition, it's also provably backward stable. That's the main improvement. Okay, so let's go back to, okay. So how do we exploit the structure of the companion matrix? The companion matrix is quasi-separable, clearly, but it's not a good idea to use the quasi-separability structure of the matrix directly. So what everybody does, what is perhaps smarter to do, is to decompose A as a unitary matrix, think keeping the subdiagonal and putting a 1 here, okay, and forget the coefficients. This is a unitary matrix, right? Plus a rank 1 correction that contains the coefficients with a -1 here, right? And unitary plus rank structure is nice because it's preserved by the QR iteration. Whereas for the quasi-separable structure of the companion matrix, things are a bit more involved. Indeed, if I take a matrix in this form and I multiply it on the left by Q star, on the right by Q, which is, as we saw, the basic iteration in the QR algorithm, what happens is that we have again a unitary plus rank 1 structure, right? This is unitary, this is a vector times a vector, row vector times a column vector. Moreover, we can easily see from the upper Hessenberg structure of A, the unitarity of U, and the nullity theorem. So everything we said before for the structure of our upper Hessenberg unitary matrix, this is upper Hessenberg, so plus a rank 1 correction. Then we get a quasi-separable rank structure for the U factor that has rank 1, or the quasi-separability, or the 1, but actually it's really rank 1 in the lower triangular part, starting from the second subdiagonal, so the green part here, and we have quasi-separability order 2 in the upper triangular part. And so we can use quasi-separable representation of this kind. I hope it's easy to see it. So each entry of our matrix A at this point is represented in a quasi-separable way. So look, for instance, at this entry. This is entry 1, 3. And so it's represented as G1 times the 2 matrices times H3, which is a column vector, plus the rank 1 correction. And the same holds for all other entries. And then the bulge chasing algorithm is adapted to this representation. So what we do is we work directly on these generators. I won't show you the details, which are a bit technical. So one drawback of structural linear algebra is that sometimes it can be a bit technical. So in order to follow the algorithm, you need a little patience, and I won't go into the details, but really what you do is work on these generators, apply the 2x2 unitary matrices on the left, on the right, and update the generators. Okay, so as input we have, as input of each iteration, we have the generators of the matrix, and as output, the generators of the matrix, the updated generators of the new iterate. And then, of course, we also update the perturbation vectors. And this is easy because we just apply Q and Q star. So numerical experiments show how this approach is actually n-squared in practical applications. So in these examples, I'm using polynomials with random coefficients, chosen uniformly from 0, 1. And in this example, I'm looking at the cyclotomic polynomials. So z to the power n minus 1, minus I, sorry, minus the imaginary identity. And in these pictures, you can see in red and blue the timings for structured versions of the QR algorithm for these polynomials, these random polynomials, with degrees that go from 50 to 300, okay? And in green, the timings for LAPACK, for a standard general purpose cubic complexity implementation in Fortran. And you can see clearly that whereas for low degrees, there isn't much improvement, or maybe there isn't an improvement, but there's a degree here where the structured version overtakes the standard one. And at that point, you can see very clearly how the cubic growth is very different from the growth of the timings for the structured version, which is indeed quadratic also from an experimental point of view. Here we have a logarithmic plot of timings for, again, random polynomials with degrees from 100 to 2000, okay? So the blue diamonds are timings in log, okay? And you can easily see that they are nicely lined along this line with coefficient 2.01. So it's really a quadratic complexity. So the numerical experiments support the complexity analysis, and the errors also experimentally tend to be quite small. So I still have so more direct methods. So the point is, even though iterative methods in themselves can be less expensive, but the point is it's hard to know from the beginning how many iterations you're going to need. For instance, Newton iteration, where do you start for Newton iteration? It's hard to predict how to choose starting points for your roots. There are results. There's very interesting results on possible choices of starting points for Newton iterations that guarantees that all roots will be approximated. But you have to start from many roots, from many initial points, and on one hand, this might not be computationally interesting. And on the other hand, it's sometimes hard to say when two initial points are converging to the same roots. Are you converging to the roots that are close, or are you converging to the same roots? So methods that use iterative approaches usually apply a combination of techniques. So there is typically one main iteration used for approaching the roots. And there are or should be inclusion and exclusion results that allow you to pinpoint clusters of roots. So you should be able to say when an approximation you have found is actually an approximation for an isolated root, or it could be an approximation for a cluster, and then you need to be more accurate and look more closely at your cluster, and then use Newton iteration for refinement because it's fast. So estimating the complexity is not always easy. What I can tell you from an experimental point of view is that there's a very efficient solver that's called MP-solve, and applies iterative methods. It's based on, a combination of techniques, actually. It's mainly based on iterative methods for approximating roots of polynomials with any desired accuracy. And for now, it turns out to be faster than all structural implementations of eigenvalue computations. So the iterative approach for now is still advantageous. We don't know if maybe in the future it will be possible to use a combination of these methods, or to further improve structure QR in order to have an even faster approach. But as far as I can tell, that MP-solve for now is still a bit faster than structure QR. It's also been implemented with care, and also there's an app available for MP-solve, by the way. If you're interested, you can download it on your phone. So if you find yourself standing in a queue and you have nothing to do, you take your phone and you can start, take out your phone and you can start computing roots of polynomials. It's something, right? You sometimes feel the need for computing roots of polynomials, know what to do. But what I'm saying, it's good to develop many avenues of research for the same problem, and you never know what's going to happen. So, and besides, even though the final result is not as fast as other methods, but still fast, it can also open the way, pave the way to further developments in other directions. So you're trying to solve a problem, you develop a technique that can prove to be useful in other contexts. So you never know. So this line of research, for instance, has given rise to many useful techniques that have been applied to other settings. Besides, I'm only talking here about roots of polynomials, but actually these approaches generalize to many other problems. So computing eigenvalues for different kind of structure matrices, different kind of companion matrices, and generalizations to pencils and linearization of matrix polynomials. And this is related to many kinds of applications that cannot be solved in a standard way so simply, at least, let's say, by iterations. So in this specific problem, QR is still not competitive, but it's interesting if you look at the whole picture. Okay, so let me just say a quick word about the approach to structure QR that uses core transformations. So core transformations is a fancy term that means basically 2x2 unitary matrices embedded in a bigger identity matrix, like the ones we saw before. Okay, so you have your matrix, that's an identity. And at some point you have a 2x2 matrix, and then you carry on with your identity. And this kind of matrix, we're going to call it, well, some letters say K, I, where I is the index at which we place the active block, the unitary block. So such a matrix is going to act on rows I and I plus 1 of a matrix if we multiply by left, or columns I and I plus 1 if we multiply from the right. So the idea in this approach is that you store matrices in QR form, so as a product of unitary times upper triangular, and each of these factors in turn is broken down as product of core transformations. So let me explain a bit more in detail. Okay, so for the special case of the companion matrix, then the authors have developed a general framework that works also for other cases. But let's look at the companion matrix. The companion matrix is represented in QR form. So this is a factorization of the Q factor. Okay, so if A is equal to QR, this is a factorization of the Q factor because A is upper Hessenberg. So when you reduce it to triangular form, basically what we apply is a sequence of 2 by 2 matrices that put 1, 0 at a time in the subdiagonal. So that's why you can factorize Q in this way. And then the triangular part, the upper triangular part, is factored as a product of all these 2 by 2 co-transformations, where the CIs, these co-transformations, are chosen so that they roll up, they put zeros in the rank 1 part. So roll up. The rank 1 part. Okay. When we perform this QR transformation, we are left with an R that clearly has this kind of form with a vector here, okay? And the way these transformations are chosen is in order to roll up this vector, to put zeros here until we're only left with a non-zero as the first entry. And then the BIs are chosen as to make everything work, to make the factorization work. Okay, why is this a good approach? Because at this point, we're able to apply the QIs, the 2 by 2 transformations of the QR iteration, by shifting them through this representation. What does this mean? When you have co-transformations and you multiply them, there are 3 possibilities, basically. Either you have 2 co-transformations that commute because the active blocks are far away, so you can exchange them. Or they could be co-transformations that act on the same rows and columns. So they have the same index. In this case, you just multiply them, you obtain again a co-transformation. This is called fusion. And then there's an important operation called a turnover or shift through, or there are many names. When you have to multiply 3 co-transformations with indices I plus 1, and I. So this way, okay? I, second matrix is 1 index lower, third matrix is back 1 index up, like this. This kind of matrix, if you develop the computation, it's a full matrix, but you can factor it again in this way. Okay, again, as a product of 3 co-transformations, but this time you reverse the indices. So this acts on I plus 1, I plus 2, this on I plus 1, and this on I plus 2, I plus 2, I plus 1, I plus 2. Okay, and why is this nice? Because because when you act on such a matrix, you can happily forget about the rank 1 part, which is already encoded in these matrices, which have been chosen as to roll up the vector, so they somehow contain the information hidden in this rank 1 part. And then you use these operations to apply the QIs, each bulk chasing transformation to the structure. Okay, because each time you apply a QI here, what you do is, well, you look at the transformations you encounter here. If you can, you apply commute or fuse. And when you find a matrix with which you cannot commute or fuse, you can apply a turnover. And in this way, this matrix Qi, this transformation Qi, will work its way, will be able to walk along this factorization and help us implement the bulk chasing process. Okay. And this turns out to be stable because it's based on unitary transformations. So the intuition here is to forget about the rank 1 part and only work on the unitary parts. Okay. So I'll just say 2 very quick words on error analysis. So what about error analysis for this kind of approach? There are 2 things we have to consider. One is stability, is backward stability of the QR algorithm. And another one is the backward stability of the QR algorithm as a root finder, that is to say, with respect to the coefficients of the polynomial. Okay, so backward stability as an eigensolver means yielding eigenvalues, exact eigenvalues of a matrix that's close to the original matrix. Stability as an eigensolver, as a root finder, means yielding the roots, the exact roots of a polynomial that's close in norm to the original polynomial. Okay. So QR, unstructured QR is known to be backward stable. And there's a classic, very, very fascinating work by Eden and Murakami, which characterizes the backward error of QR as a root finder. And so what we find is that the distance between the original polynomial and the polynomial that has as exact roots, the roots computed by QR, is machine epsilon, of the order of machine epsilon, times the square norm of the polynomial. I mean the norm of the coefficient vector of the polynomial. What about a structured case? So in the quasi-separable case, unfortunately, even though the numerical approach seems sound and experiments are satisfying, there are little results on theoretical results on stability. On the other hand, the big improvement that comes from the co-chasing approach is that one is able to prove backward stability. And in fact, not only it holds that this version of QR is backward stable, so it gives us a final matrix A hat that is unitarily similar to a matrix that's close to the original one. But it's also possible, if we look at the root finding problem, to establish this backward error bound that tells us how this method is stable also as a root finder. And it even has a better condition, a better bound than unstructured QR, because there is no square here. Okay, so this is a very interesting result in this respect. Generalization, as we mentioned, and related work includes the problem of reducing a matrix to Hessenberg form and generalizations to pencils and matrix polynomials. So I won't say much about this. Another possible generalization includes changing the basis of the polynomial. So let's not use monomials, but let's use something else, for instance, Chebyshev. And in the Chebyshev basis, we have other forms. In other bases, we have other forms of companion matrices that still retain some kind of structure. So, for instance, in the Chebyshev case, we have this almost Hermitian plus rank 1 structure that can be exploited in similar way to what we have seen. Okay, so that's all I wanted to say for today. Thank you for your attention. Thank you. So tomorrow we'll have the second part and we'll talk about functions of matrices.
So Paola, thank you. It was really a wonderful talk. It seems like maybe the chair has a problem with getting the maybe back his microphone on. This is Evelyn talking.
Yes, yes.
I just wanted to feel
Hello,
a bit void
Evelyn.
of you feeling so lonely here. I assume that
Thank you.
some chair is going to, because I don't think I can unmute people. Maybe let me just ask, is there some question? And maybe people can just unmute themselves and ask the question. Oh, here is Jean-Claude.
Yes. Jean-Claude, we don't hear you. Can you please try? Are you muted? Thank you, everybody. You're too kind. Jean-Claude, we can hear you. Should I do something with the presentation or?
Okay, maybe we can take one or two questions, or you can ask your question.
Maybe in the chat, yes.
Yeah, in the chat or
Okay.
later.
Or maybe during the pause, yes.
Yeah.
Maybe it's easier because I don't want to take too much time from the pause.
So maybe we can take the break now, and if you have questions, save them for the next session or something like that.
Okay. So do we stop the recording here? I'm not sure how it works.
So I will pause the recording. So thank you, Paola, for this talk. And so we make a break. We start again at 11. And please come back like 2 minutes before so that we can start at 11. Thank you again, Paola.
Thank you. Thank you. I see a question here. Going back to slide 7. Okay. Please feel free to leave, of course. But so, is there a faster way to go back?
Yes, you can select slide 7.
I can select. Oh, good. Slide 7. What is a Z parameter? Wait. Oh, NZ. Yes. This is just a standard MATLAB notation. So when you plot the sparsity pattern of a matrix, okay, what MATLAB does, it's nice, I think. So it plots the matrix as a square with blue dots every time the matrix has a non-zero entry, and nothing if there's a zero entry. So you can see clearly what shape the sparsity pattern has. And NZ is a number of non-zeros. So what it says here is that there are 40 entries which are non-zero over 15 squared, so 225.